All right, welcome to our presentation on Gibbs free energy. So basically, we should probably start off with defining what is Gibbs free energy. And basically, when we talk about Gibbs free energy, it's combining enthalpy and entropy to determine whether or not a reaction is in actual fact going to be spontaneous or not. And so defined, we would say that it is a combined enthalpy, entropy function that determines the spontaneity of a reaction. We also use this to look at the amount of free energy available to do work within a system, right? So let's say that as well, determine the amount of, and I'll just change my pen color here because this is important, free energy available within a system or to do work. Okay, so really important concept to understand. So we've looked at enthalpy, individually, and we've looked at entropy individually. Now we're going to combine the two to actually determine whether or not a reaction will be, in fact, spontaneous. So let's just define it in terms of its mathematical construct. So we know that delta, just gotta go down here. So we know that delta means change. So delta G naught is equal, in this particular case, to delta H naught minus T delta S naught. And let's have a look and see what these means here. So this means, of course, delta, and that means change of. And G is Gibbs free energy. H is your enthalpy. And T is your temperature. And S is your entropy. And of course, this is your standard conditions. That means, delta S naught, delta H naught, delta G naught. And so when we talk about standard conditions, we're really talking about 1 atmosphere, 1 molar, or 25 degrees Celsius, or 298 Kelvin. Okay, so basic life conditions here. All right, so again, so this delta G is equal to the enthalpy of a reaction minus the temperature times the entropy of that particular reaction. Now, also, we should probably know the units that are associated with that. And when we talk about delta G, we're talking about energy units, measurements of energy. So usually we talk about it in terms of kilojoules, but you might see it in terms of joules, or you might see it in terms of calories. Okay. When we talk about enthalpy, I'm going to change this just to make the color a little bit different. We talk about enthalpy in terms of kilojoules. When we talk about temperature, we're going to be looking in terms of Kelvin. And when we look at entropy, it's going to be in units of kilojoules per Kelvin. Now, keep in mind that if you look at this unit here, and this unit here, in this particular case, they're all in kilojoules, which is great. But if one's in joules, then you need to be able to convert that, or in calories, you need to be able to convert that and have all 3 units the same. The same is true when we talk about temperature. So here's Kelvin, and here's Kelvin as well. So if one is in degrees Celsius or in Fahrenheit, then you need to be able to convert those into Kelvin. And we use, we use Kelvin because, of course, it's going to always be a positive value. And of course, you know that of absolute zero. And we'll touch more on that later on. And that positive value makes a difference when we're actually looking at how temperature affects enthalpy and entropy, or the free energy of this system. Okay, so moving on here, let's take a look at an example. So let's say we have, I don't know, let's say we're delta H. So I'm going to change my pen here. There we go. So delta H in this particular case, let's say that that's equal to negative 900 kilojoules. And your entropy in this reaction is equal to negative 400. And I'm going to change the pen color here just to, you don't forget that this is in joules here. So we want to make sure to adjust that. And your temperature is equal to 298 Kelvin. Well, this is equivalent to about 25 degrees Celsius. So what we're going to do is we're going to plug this into our formula. And what is our formula? Well, our formula is delta G is equal to delta H minus T delta S. And of course, these are all not, if you want to put those there, just all standard state conditions, 25 degrees Celsius. So now we say that this is equal to, it's going to be negative 900. And I'm just going to keep the units off for simplicity here. The temperature is 298 Kelvin. It's already given you that. And look at the entropy. It's in joules. So what we want to do is we want to convert that to kilojoules because this one's in kilojoules. Okay. So we're going to just simply move the decimal 3 places here. So that'll be times 0.400. And you should get an answer that says that it's minus 780.8 kilojoules. So notice that kilojoules is what we're left with, which is the requirement for, Gibbs free energy. And this is actually good because our delta G here, the delta G for this particular reaction is negative. And because it's negative, that means that the reaction will be, in fact, spontaneous. So very, very important concept to understand this, this construct right there. All right, let's move on and have a look at perhaps, we're going to look at this in terms of exothermic and endothermic reactions. And we're going to look at this and relate that to enthalpy and entropy. And then we'll introduce the temperature construct as we go along here. So first things first, let's have a look at exothermic reactions. So this is going to be an exothermic reaction. All right, and we'll just underline that. So what's an exothermic reaction? Well, let's start off with just a quick diagram of it, and then we'll look from there. So this is your, let's see here, perfect. There we go. Okay, so when we look at an exothermic reaction, basically we're looking at a reaction that will be spontaneous. It's going to go to completion, and we're going to start here with the reactants being at a higher potential energy than will the products. So just to label these here, this is going to be your energy here. In this case, you forgot about potential energy diagrams. This will be your reaction coordinate here. And this here is going to be your reactants. And this will be your products. Now, to determine the difference between these, if you notice that we start off at a high potential energy here, and you need a little bit more energy to get this reaction going here. Now this area here, between the initial reactant's potential energy and the amount of energy to get the reaction moving, this is actually termed the activation energy, okay? But to find out exactly how much energy is in the reaction, we take the difference between the reactants and the products. So your delta H for this reaction here is going to be reactants minus products. And notice what's happening here is that you're starting at a high potential energy and you're ending at a very low potential energy. So what's happened, if you think of this in terms of a ball, say we put a ball right there and we just let it go. Well, as it's sitting here, it has high potential energy, and then it follows the natural gradient or the slope down, and as it's moving down, it's doing work, and its potential energy is converted into kinetic energy, and it might, be given off as heat and sound and whatever it might be. By the time it gets to the bottom, though, it has a much lower potential energy, and it'll do this naturally. You won't, without work being done or interference of outside forces, you won't see the ball moving uphill, up an incline. Okay, so basically, let me just change my pen here one more time. If we have a reaction that looks like this, say we have A plus B, then it's going to end up forming, the product C plus, and this is the key here because it's an exothermic reaction, energy. And notice that I put the energy on the product side. All right, so that's one of the ways we can certainly look at this. And this energy will be given off into the surroundings or into the universe, okay? So what do I mean by that? Well, once again, let's have a quick look. I'll just draw a couple diagrams here. So let's say we have a box here. And this is just a review from what we've done before. And I'm going to, let's make that box. Yeah, let's make it blue in color here. And I'm going to come back up and I'm going to put another diagram inside there. And let's put a circle right there. And I'm going to make that guy, let's go with a light green. There we go. If it lets us do it. Okay, maybe not quite bright enough here. Let's try this. There we go, we'll just go with white. Okay, so now I'm going to simply just label these. So starting over here, this is actually going to be the surroundings here. And this guy down here is going to be our system. And I want you to notice that this entire, surroundings plus system is going to be our universe here, okay? So we know that the total amount of internal energy of the universe is equal to the sum of the total internal energy of the system plus the total or change in total internal energy of the surroundings. Okay, so U just simply stands for internal energy, and that's the total amount of energy, total kinetic and potential, and all the different forms of it, and so on. Okay, so in here, on an exothermic reaction, what's actually occurring is we see a system, and we talk about the system from the enthalpy point of view, and we talk about the surroundings from the entropy point of view, the entropic point of view. So in an exothermic reaction, we see that the delta H of the system is going to be negative, and that means that the system is giving off energy into the surroundings, just like this. And according to the first law of thermodynamics, that energy is neither going to be created nor destroyed, it's only going to be transformed. And so the total amount of energy in this universe, this confined area here, is equal to both the systems and the surroundings. So if we lose energy from the system, that energy must be gained by the surroundings. So if it's increasing the amount of heat energy in the surroundings, that means that the molecules have more energy, more kinetic energy, so there'll be more collisions, more rotational, vibrational, translational energy, that kind of stuff, transfer of energy, and there'll be more disorder and chaos. So your entropy of this particular system is going up, and because the disorder is going up, the entropy is therefore positive. All right, and so it is this sort of system that will occur naturally, and it is this sort of system that in fact will be, yes, spontaneous. All right, so let's move on and let's have a look at what we mean by exothermic reactions. And once again, I'm just going to change my pen color here. So let's look at an endothermic reaction. And I'll just underline this again. And I think we'll stick to the same format that we did last time. We were looking at drawing energy diagrams for these here. So let's do the same thing here. So in this guy here, I'll just draw a potential energy diagram. Put that there, and we'll put that there. And I'm going to change my pen color here a bit, just to make it a little bit more fancy. Now, in an endothermic reaction, what's actually occurring is the opposite, of course, of an exothermic reaction. So in an endothermic reaction, you're starting actually with a low potential energy in the reactants. Oh, gotta change my pen here. There you go. With a low potential energy in the reactants, and then that's going to increase in its potential energy and eventually plateau off into the products. Now again, this is going to be our reactants here. And this will be our products here. And this area between, let's just do it this way. This area between here and here is your actual activation energy, the amount of energy required to get the reaction going in the forward direction. And in order to find out, what the enthalpy of the reaction is, it's going to be the difference between the products and the reactants. So the enthalpy of the reaction will be products minus reactants. And because it's an endothermic reaction, you gain energy in this process. Therefore, this will be plus. Okay, so it takes work. It takes energy to make this reaction occur. Now, going back to our ball analogy, let's say we have a ball here, and we want to see if this ball will be spontaneous to going up the hill. In other words, will it occur on its own without outside work such as wind or whatever it might be? And the answer, of course, is no. In order to make this ball go up that incline, work needs to be done on the ball. So, you're going from a low potential energy, and it's, work's being done, and you end up at a high potential energy at the top. But in order to get there, you have up this natural incline, you had to do work on the system. So in this particular case here, what we have occurring is we have A plus B plus energy, and that's going to produce your C, your product. And so this energy is put into the system in the form of work or whatever it might be, and that, so in order to produce a product here, you had to put work into the system, and so this will be at a higher potential energy. All right, so I think that's probably a good start here. Just maybe one other thing to mention here is something you haven't taken yet, but something you will be looking at fairly soon in these reactions, and that's K equilibrium. Now, I'm just going to go back here for 1 second here and open up the last slide. So this is an exothermic reaction. So in terms of an exothermic reaction, we say that in terms of K equilibrium, that K equilibrium will be greater than 1. And what does K equilibrium mean? Well, as you'll learn in the next while, the K equilibrium tells us basically where the reaction is at equilibrium along the pathway. So is it more on the reactant side or is it more on the product side? And if so, how far along is it? So in this particular case here, K equilibrium for an exothermic reaction basically tells us that the concentration of the products will be much greater or greater than the concentration of the reactants. So if more products are forming than reactants, it is going to be spontaneous. Okay. On the other hand, if we look at the last one, the last diagram here, the K equilibrium, is going to be less than 1. And that tells us that, in fact, the products will be less concentrated than the reactants. Okay, so it'll be spontaneous in the forward reverse direction, okay, but not in the forward direction. All right, so let's have a look at this guy in terms of a couple diagrams perhaps as well. So we'll start off here. We'll just quickly draw our rectangle, and I'll fill that in here, and we'll make this one, let's make it orange. Well, that's not really orange. Let's change that. Let's make that more, yeah, let's try that. Okay, so then, inside there, we're going to put our circle. Just like this. And we'll make that guy, yeah, let's see here. Let's make that one, we'll make that one yellow. Okay, so the same, same concepts are happening here. So this is going to be your, gotta change this 1 second here. There we go. So this is going to be your surroundings here. And again, this is going to be your system here. And in this particular case, your delta H is going to be, well, it's going to be positive. So that means that the system is the surroundings is losing energy to the system. And because of that, the system itself has become positive. It's increasing in thermal energy, right? And as it does that, the atoms in here become more chaotic and there's more disorder because of the more collisions. So the entropy in the system is increasing. But notice that the entropy in the surroundings is decreasing. So delta S here is actually decreasing. So because it's decreasing, we say that entropy is negative from the surroundings point of view. There's less disorder, more order, less randomness, more order in this area here. So anyways, I hope that makes some sort of sense there. So this sort of reaction is, we say I'm going to change my pen here. It's going to be non-spontaneous. Okay, let's look at another example. So is this reaction going to be spontaneous? This one here, and I'll put a big question mark, and you tell me. So we have a delta H, and that delta H is equal to 203 kilojoules. And say we have a delta S, and our delta S is equal to negative 195 joules, okay, per Kelvin. And we have a temperature that is equal to 273 Kelvin. So right away, looking at this equation here, looking at enthalpy and entropy, I want you to notice that the first thing to look at is that the entropy in the surrounding medium is going to be negative. And so it's tending towards more order, less disorder. So right away you should kind of think that, well, that's not right, because if it's going to be a spontaneous reaction, it has to be more disorder, because those molecules are going to be slamming together and colliding at much faster rates, and there's just more chaos and things happening here. So you'll have more translational and rotational motion here, and they'll be vibrating back and forth. Anyways, and our enthalpy is wrong as well, because the enthalpy should be negative from this system's point of view. But let's do this. Let's work out the calculation and see where that takes us. So we know that delta G is equal to delta H minus T delta S. And this is going to be equal to, well, delta H is 203 kilojoules minus, now notice that this is in joules, and we want to make sure that all these units are the same. So this is actually going to be 0.195 kilojoules per Kelvin. So that's going to be 0.195 kilojoules. Oh, I was not going to include those units, but we did here, so let's just keep going. Per Kelvin. And of course, the temperature is going to be 273 Kelvin. All right, so at the end of the day, when you've done your calculations, you'll find that this is in fact a positive number, which is 122.4 kilojoules. So this is endothermic, so the delta G is positive, and because it's a positive delta G, it tells us that this reaction, in fact, will not be spontaneous reaction. So what's the takeaway so far? Well, so far we know that we've inferred that if delta H, if it's less than 0, so it's negative, it'll likely be spontaneous. And if your delta S is greater than 0, from the surroundings point of view, and this is a system, the surroundings point of view here, it'll likely be spontaneous. However, this by itself will not tell us for sure whether or not the reaction is spontaneous or not spontaneous. That's why we have to combine these. Okay, let's move forward to the next slide. So, here we go. Okay, and we'll come back and we'll put one this way. Okay, I think that's probably pretty good. So now I'm going to go to my black color here, and I'm going to put in this quadrant here, I'm going to put a positive delta S. And down here, I'm going to put a negative delta S. Up here, I'm going to put a negative delta H. And over here, I'm going to put a positive delta H. So what we're doing is we're going to find out what are the different situations that can occur in our closed universe. Okay, so anytime that you have a negative enthalpy and a positive entropy from the systems and surroundings point of view, you will have a spontaneous reaction. So it'll be spontaneous always from that point of view. Now, if you have, from the surrounding point of view, a negative delta S, so the order is increasing, and from the system's point of view, you have a positive delta H, so in other words, it's absorbing enthalpy, the spontaneous reaction will never occur in this particular situation. Now, there's two other situations we need to look at, and that is if you have a positive delta S from the surroundings point of view, which is good, it's favorable, but the enthalpy of the system is also positive. Now, the only time that this is going to be spontaneous is it's spontaneous only at high temperatures. And I'll show you what I mean right here. So give me 1 second to just write this out. So our delta G is equal to delta H minus T delta S. Now, in this particular case here, we know that the delta S is positive. And I'm going to just leave temperature off here for a second. And we know that the delta S is also positive. So notice what's happening here. You're going to have an enthalpy which is going to be positive, and you're going to have, you're going to multiply the negative times the positive here. So this is actually going to become negative here. So you want to have, at the end, you want to have your delta G as a negative value. So the only way you can ensure that you have a negative value is if the temperature is extremely large. So this number this together has to dominate this, because you want to have a negative number at the end. So that's why we say that when you have a positive entropy in the surroundings and a positive enthalpy in the system, it can be a spontaneous reaction given that the temperature is high enough that this side of the equation dominates the enthalpy. So in this particular case here, the entropic or the entropy is important and the enthalpy is not important. All right, so coming down here, now one more time. Now we have a negative delta S, which is not favorable, and we have a oh, sorry, right here, and we have a negative delta H, which is favorable. So in this particular case, it will be spontaneous only at low temperature. Okay, let me once again see if I can put some clarity to that. So say we have delta G here, and delta G is going to be again equal to delta H minus the temperature delta S. All right, so in this particular case, this is good, this is favorable, minus, and in here, notice what's happening is we have, once again, a negative value. So a negative times a negative is a positive. That's bad for our delta G. So what we want to do is we want the enthalpy to dominate here. We want this to be the dominant. And the reason we want that to be the dominant is it's the negative number. We want the negative number to dominate the positive number because we need a negative number to have spontaneity in the reaction. So in this particular case, in order to have that negative number, enthalpy becomes important, whereas entropy in here is not as important. Okay, I hope that makes some kind of sense. All right, so I'll try and give a little bit of understanding as to kind of what's going on here. So when we talk about these sort of situations here, let's say we have some reactants. I don't know, maybe we have these guys out here, and they're floating around, they're kind of doing their thing, and they're going to end up forming products that have higher order. They have structure, just like that. So you're going from increased disorder to increased order. All right, so what happens here is if we look at this particular situation here, where we have, the enthalpy is positive, so it's being put into the system, and of course the entropy is also positive, so there is disorder over here, and if we increase the temperature of the system enough, that means that these guys that have some kind of structural order here are going to be slamming and combining, and if the energy is high enough, they'll actually break apart or reform different molecules, but they'll reform this way to increase the disorder of the system, and thus it'll be spontaneous. But you have to increase that. Now, at low temperature, these guys might come past each other and they might bump into each other and so on, but they never do it with enough sufficient force to overcome, to make these actually, collide and form new molecules, to overcome that activation energy barrier. Anyways, that's kind of the, in a very, very roundabout way, what's occurring here. Now, in our next video, we're going to look at the calculations involving enthalpy, entropy, and Gibbs free energy. Thanks for watching.